Welcome to Land Eco Lightning Talks and Thinking Like a Landscape with Dr. Kevin McGarrigle. In this three-part series on working with landscapes, in part one, I discussed the importance of specifying a pattern process question. In part two, I talked about the steps involved in formally defining a landscape based on that pattern process question. And in this part three, I'll talk about the importance of landscape definition. Okay, let's get started. Recall from the previous presentations in this series that there are myriad potential landscape definitions for any given pattern process question. The same real-world area can be represented by many alternative landscape definitions, all of which depend upon the specific pattern process under consideration. So for example, in this example shown here, I might represent the real world based on continuous percent canopy. Or alternatively, I might represent it based on continuous canopy height. Or I might represent it based on terrain, such as aspect, classified into several categories. Or I might simplify it and represent it as a binary mosaic of canopy and non-canopy, or perhaps canopy and non-canopy with roads and streams superimposed as fragmenting features. The point here is that the same real-world area can be represented in myriad different ways depending upon the specific pattern process question under consideration. I want to make several important points about why landscape definition is so important. First, measures of landscape pattern can be highly sensitive to alternative landscape definitions. In the example shown here, I've defined the landscape in 30 alternative ways. These 30 alternative landscape definitions involve making different choices in each of the steps involved in the formal landscape definition. In this particular case, keeping the conceptual model constant, in this case using the patch mosaic model, but changing the thematic content and resolution and changing the spatial grain and spatial scale, and including fragmenting features or not. So considering 30 alternative combinations of these things to represent the underlying pattern of the landscape that I would then relate to some process of concern. And as you can see in the figure on the lower left, which represents the alternative landscape definitions along the x-axis and number of patches as a very simple measure of landscape configuration, we see that the variation across landscape definitions is huge. There are orders of magnitude changes in the number of patches based on differences in landscape definition. And it's critical to understand that the landscape pattern as measured by this or any other metric cannot be interpreted independently of the landscape definition, because the value that we derive is entirely based on the landscape definition. The second point is that measures of landscape pattern differ in their sensitivity to landscape definition. So the figure on the left is the same figure we were just looking at, with the 30 landscape definitions along the x-axis and number of patches as a fairly simple measure of configuration, showing a high degree of sensitivity to landscape definition. The figure on the right shows the same 30 landscape definitions along the x-axis and a simple measure of landscape composition, the Simpson's Diversity Index, showing much less sensitivity to landscape definition. In fact, most of the alternative landscape definitions lead to only minor and probably trivial differences in the computed value of Simpson's diversity. And really, there's only one major change among definitions that lead to non-trivial differences in Simpson's diversity, shown by the differences between the first 15 bars and the second 15 bars. In general, what we find in practice is that the configuration metrics are generally more sensitive to landscape definition, and especially those metrics that are sensitive to the inclusion of small patches. So for example, metrics based on mean patch characteristics, such as mean patch size, tend to be especially insensitive to landscape definition choices that involve including or excluding the smaller patches. So one must pay particular attention in defining the landscape when choosing configuration metrics based on means that are going to be very sensitive to the inclusion of those smaller patches. The third point is that pattern elements can differ in their sensitivity to landscape definition. So in the previous slide, we talked about how the metrics, the measures of landscape pattern, can differ in their sensitivity to landscape definition. Here we're talking about the actual pattern elements within the pattern. These can also differ in their sensitivity to landscape definition. And in general, what we find is that the rare classes, those that have very low level of occurrence or representation in the landscape, and linear features, those that are linearly configured, can oftentimes have a disproportionate importance on landscape function, hence the reason for including them in the landscape definition, but they tend to be more sensitive to choices made regarding the spatial resolution when defining a landscape. So for example, if we coarsen the spatial resolution, in this case from 30 meters to 60 meters, some of the rare classes, the rare patch types, essentially disappear and are lost from the final landscape. And if these are important features or elements to include in your pattern to relate to your process, then we have to be particularly careful about changing the spatial resolution of the data. The third point is that some pattern measures can be misleading with some landscape definitions. So one needs to be particularly attentive to how they define the landscape and the choice of metrics for measuring the pattern in that landscape, and whether there are potentially any misleading relationships or interactions. And this is best illustrated with an example. So in this case, we might represent the landscape pattern based on vegetation types, whether those be based on differences in vegetative community types or vegetative structures, doesn't really matter. But if we have a landscape where the pattern is depicting some aspect of vegetation types or structures, and we're concerned with the continuity or the connectivity across the landscape, so that areas that extend for greater distances within the same vegetation type or structure class would be deemed more continuous or more connected. If we were to superimpose roads on that landscape as a fragmenting features, and we were to measure connectivity or continuity with the connectance measure, which is a measure of the average or the proportion of patches of the same type that are within a certain threshold distance, so that as the connectance measure goes up, presumably patches are less isolated from each other, that there's greater connectivity or connectance between patches. If we add roads, the connectance measure actually decreases because patches appear to be closer together. So a greater percentage of the patches end up being within that threshold distance. And so the connectance measure actually increases when in fact connectivity in the real world decreases. So we end up with a counterintuitive and misleading relationship here. And it's not because of anything that's fundamentally wrong with the landscape definition. It's just how that landscape definition interacts with this particular metric. The point here is that one always needs to pay attention to how the chosen landscape definition may be interpreted differently or potentially misleadingly with different landscape pattern measures. So given these points, there's some important implications. First, that given the sensitivity of pattern measures to landscape definition, it behooves the user to choose a parsimonious suite of complementary metrics. And by that, I mean that no one metric is going to paint a complete picture of the pattern process relationship, especially given that any individual metrics could actually produce misleading results. So it behooves the user to choose a suite of metrics, ideally complementary metrics, each of which says something different than the others, and as a package, as a suite of metrics, paints a more complete and comprehensive picture of pattern. But one also wants to choose a parsimonious suite of metrics. That is, choose the fewest number of metrics that yet will still provide a complete, comprehensive picture of pattern. So on the order of a few to several, but probably not dozens of metrics. And given the sensitivity of pattern measures to landscape definition, a comparative framework is often the best used. So for example, once we've defined the landscape, if we were to measure the pattern based on a parsimonious and complementary suite of metrics, such as shown here in this table, we might be left wondering how to interpret those values. Are these values good? Are they bad? In some cases, it's very hard to know how to interpret those values because we have no reference. If the landscape definition is held constant, one way we can gain interpretive value is by comparing that landscape definition under alternative scenarios. So for example, as shown here, we might define the landscape similarly. In other words, we make the same decisions with regards to the conceptual model, thematic content and resolution, spatial grain, extent, fragmenting features, etc. But then we evaluate the pattern under different scenarios. In this case, in the figure, the gray bar on the lower left shows the range of values for the contagion metric, a measure of overall landscape clumpiness, under the historic range of variability scenario. So as a reference framework, we have simulated what we expect the contagion metric to be under historical conditions and derived the range of variability. And as you can see here, it ranges from roughly, let's say, 32 to 35. And while we don't really have a way of knowing is 32 to 35 a good value for contagion or a bad value, and we're not really confident in the accuracy of those estimates. In other words, we could be off by 10 or even 20 units. It's very hard to know. What we can do is hold that landscape definition constant, but apply alternative scenarios. In this case, actually 8 different management scenarios where we have treated the landscape in different ways, and under each scenario measured the range of variation to be expected under that scenario for the contagion metric. And what we can see here now is that we can compare in a relative sense how each of these scenarios performed. And in this particular case, the M7 scenario came very close to approximating the HRV scenario. And again, while we're not confident in the absolute values of contagion for any of these scenarios, we are fairly confident in the relative differences among these scenarios. So this depicts the idea that if we hold landscape definition constant and we lack confidence in how our choices in landscape definition are going to affect the metrics, what we can do is hold that landscape definition constant and put our faith in the comparative values of the metrics under different scenarios. This is just another example of the same idea. In this case, looking at metapopulation extinction probabilities for a marbled salamander metapopulation in central Massachusetts. And the figure here depicts several alternative scenarios where the reference scenario is given by the solid line, the lowest, the solid line at the bottom of this set of lines, which basically is essentially the ideal condition if we were to leave the landscape in an undisturbed condition, which would be ideal from the perspective of this salamander metapopulation. This is what we would achieve in terms of metapopulation extinction probabilities. And if we were to implement alternative forest management strategies that vary in the types of cuts, the locations of those cuts, and the timings of those cuts, and then evaluate the metapopulation probability extinction under each of those scenarios, we can generate these alternative curves. And the closer the curve is to the reference condition, the better, quote, better the scenario is. And what this depicts is the idea that while we don't have confidence in the actual true probability of metapopulation extinction, because that's unknown and probably unknowable, we do have relative confidence in the comparative values across these scenarios, and thus are able to choose like one scenario as better than another. So the take-home message from today's talk is that without a clearly justified landscape definition, it's garbage in and garbage out. Given the sensitivity of landscape pattern measures to landscape definition, as hopefully shown you today, defining the landscape relevant to the pattern process under consideration is the second most important step in any landscape assessment, second only to specifying a clear pattern process problem. Well, this is Dr. Kevin McGarrigle signing off from this episode of Landeco Lightning Talks. I hope this talk has been helpful, and I hope you join me for my next Lightning Talk. In the meantime, keep on thinking like a landscape.